Welcome. In this video we're going to run through how to use SciPy in a Jupyter notebook to solve some problems from the tutorials. We'll be working towards the constraint optimization problem, maximizing wealth subject to a production constraint. So first of all, like always, we need to start by loading the libraries or packages we want, so NumPy and SciPy here. And I've pasted the questions that we're going to be working on here, so we have those in markdown blocks. So the first thing we want to do is a few practice questions on how to define functions in Python. So that is going to be using the def and return commands. So the first one we're going to call sum of squared, and remember it's good to use suggestive or useful kind of names. I'm not going to do that here for the variables. These are just x and y, two numbers, and then we need the colon to start the code block. And the code block here is very simple. We're just going to straight away return the sum of those two numbers squared. So x plus y are the two numbers, and then double asterisk to the power of 2. So when I hit enter, that has defined that function, but it hasn't actually done anything in terms of doing a calculation. We need to pass some numbers, some values for x and y to sum of squared, and so that's what I've got here on the next line. So let's go ahead and do that. I'm just going to clear the output. I just noticed that I haven't cleared the output, so let's do that again, just in case you think there's anything funny going on, and we will see 25 appear again. That's pretty straightforward. We're just really doing one calculation and returning it straight away. 2 and 3 were the numbers we were asked to do, but we can make them more complicated. 14 and 3 there, so it's 17 squared. Right, next question asks us to do the same thing, but it's going to have a conditional inside the function, because we want to produce x squared if x is greater than or equal to 0 and minus x squared otherwise. So we're going to have to do two different things. There's probably a clever way that you could do this all in one line of code, but let's just make our code easy to read. So I'm calling this function my underscore neg squared, and this will just be a function of one number, and we need the colon, of course, for the code block, and it's doing that automatically in Jupyter. It just indents it when I hit return. So I'm going to do this with a large number of steps, so it's really clear what's going on. So first of all, I'm going to construct a variable which is called temp, which is short for temporary, and that will just be x squared. And then I'm going to use the conditional. So if the original x is less than 0, then we need to change the sign. So we return minus temp. In all other cases, we just return temp without doing anything else to it, and that is the whole function. So we have made a mistake here, because neg squared, I should have a d in there, and so now that runs. Remember, errors are part of coding, so you just need to have a process of going through, spotting what's wrong, fixing it up. Very rarely will everything work perfectly the right time. So minus 2, that should be 2 squared, which is, well, minus 2 squared is 4 squared, but because the original number was negative, here we need to change the sign, and so it's changed it to minus 4. And what happens if we put in 0? comes out as 0, and if we were to put in 4, it comes out as 16. I haven't written the code here exactly as specified in the question. It said if x is greater than 0, it produces x squared. Well, of course, the boundary case here is 0, and so 0 squared is 0, and minus times 0 squared is still 0. So it doesn't really make any difference which case here of the if statement we put the 0 into, though in perhaps some other problems it might be more of an issue. The final example here with the def command, I'm going to call it squares. This is a function of two numbers, and we're going to be doing three things. So first of all, we're going to be constructing x squared, and then second, we're going to be, let's make that a little neater, we're going to be constructing y squared, and then finally we're going to be constructing x plus y all squared. Going to just make that look a little neater so they all line up. So that is our code. It's not going to return anything yet because we haven't put in the return command, and this is where we're just looking at something a little bit different. We are going to return all three of those values. So if I hit enter, shift enter now, I get out three numbers. So we passed 4 and 3. So 4 squared is 16, that's right. 3 squared is 9, that's right. 3 plus 4 is 7, and 7 squared is 49. So we've got the right answer there. Now that looks like some kind of data object, and that is in fact true. So let's just see that. First of all, going to notice that you can, let's just comment out the type command. You can in fact assign a variable, in this case result, to squares rather than just printing it to the screen, and so now result has been generated, and that is of type tuple, and so the return there is in the fundamental data types of Python. And then, of course, we could construct a NumPy array or something like that if we wanted to with those data in the normal kind of way. The last question here is a bit more involved. It involves a minimization problem using the optminimize command here. So I've got the things that we need to define already set up here. So there's we need to work out the, well actually we do need, before we do anything else, perhaps to work out what the present value is of these two levels of income. So let's insert a cell below, and we want to know what 1,000 plus 648 divided by 1.08 is. And that is not correct. I've left 0 off there. Let's try that again. 1,600. Right, so that's right. So this is the present value of the income streams. So we know that we need to use that as our constraint for the amount of money that's available to be invested. And then, and so we're going to be trying to maximize consumption. Sorry, I call this an investment problem. It's a consumption problem. We're going to be maximizing consumption subject to this present value of income. So we need to put in that interest rate because we're going to use that. You could just put in the 0.08 directly, but let's use R so that we produce some code that's a little bit more flexible for the future. Now the objective here is the utility function. So the utility function here is a simple Cobb-Douglas form. So it's going to be minus, and we're going to put are variables in x, and so first period consumption x0 is times by second period consumption, so that will be x. This is the second element of x, which will be x1, and that is to the power of 0.6. So this is the utility function up here. Notice, of course, that we have 0 and 1 down here, and 1 and 2 up here because of the way Python indexes the arrays. So this is the function that we want, but we can't just do it quite like that, because that will just generate a number there, an objective, or in fact an error, since we haven't assigned anything to x yet. We need to define it as a function. Rather than using the def and return type of setup, we can just do it in place using the anonymous function lambda. So lambda colon, lambda, and then we just need to tell it x is the variable that's going to be passed, and then the colon. And so that's defined our objective function. For the optimization, we also, I should mention, of course, that it's a minimization function, so we are maximizing utility, but since it's a minimization function, we have to multiply utility by -1. So that gives us a function we want to minimize. We need to put in some starting values. This is a very well-behaved problem, so we don't have to think too hard about those starting values. We'll just put in 1, 0, and then we have to put in the constraint. So the constraint is a dictionary, which is constructed with these parentheses. It's a data type we don't use a lot, but it is a useful one because it's a paired data structure. So we start off and we have type, which refers to the type of problem that we are working with, and this is actually an equality problem, so we can put in EQ for equality. And then the next thing we need to put in is the function that we are having as our constraint. So again, we put in fun for function. That tells us the objective function. Sorry, the constraint function. This is going to be the present value line, the market line, and so that is going to be defined in place using the lambda command. So we need to tell lambda two things. We need to tell it x, what's the variable going to be inside the function, and then we need to tell it what the function is going to be. So it is that we take present plus the discounted value of future expenditure consumption. So that's 1 plus r, and then it's in the standard form for constrained optimization problems, so we minus the amount of their 1600, which is the present value we calculated up here previously. So this is our constraint. And finally, we need to pop this inside the optimization opt minimize command. So this is the minimization optimization command. So we need to give it objective, which we've defined previously. That's the negative of the individual's utility. We give it the starting value, which we defined here, the initial point. And we need to tell it that the constraint is equal to cons, which we just did here. Two different notations here for passing things to a function. You can either just put it in the appropriate position, so basically put the thing straight in with a comma after, or you can put the variable object that you're passing and tell it that that's going to a certain name. So it's going to the name constraint here. So then we run and we have an error there, and that's because I've left off S for constraints. And so now it's run. And of course, the answer is assigned to demand. And in order to have a look at that, we need to print the elements of demand to the screen. So this is two choices because there's two values for the x's here, x0 and x1. So we're going to print those to the screen using the print screen, and let's be a little bit nicer rather than just printing the numbers and actually print an explanation. So C1 is equal to the first element in demand, and C2 is equal to the second element in demand. And there we see the solutions that we've got out. Nice to put in some code here that explains what things are. And again, this is good practice because if you come back weeks, months, or years later, you might not remember which bit is which, and so it's nice to have built in here an explanation. So rather than putting it in the comments and saying C1 is this and C2 is that, we've actually just labeled it in the output. And so that's nice if we wanted to just copy that into another document or something like that. Now the final point here is just one of aesthetics. We've got a whole lot of decimal points here, which leads to somewhat ugly looking result. And it's actually reflecting here some machine imprecision, some machine precision issues, and we'd actually much rather to see this rounded off to say 2 decimal points. So finally here is some code that will do that. So the 2f gives us 2 decimal points in a floating point number, and the percentage sign tells the print command to go and look back here where the percent is given for what to insert there. So it's saying insert something, and then it goes and looks over here for what that thing is to insert. So finally we execute that, and we see C1 is equal to 1000 and C2 is equal to 648. And actually we've got rid of the issues with machine precision, getting a little tongue-tied there, by rounding, and we actually get the same exact answers as we have from doing this problem analytically, which is that consumption in the first period is equal to income, and consumption in the second period is also equal to income, which is of course not a typical result of optimization. People will typically be wanting to spread their resources around, not necessarily follow exactly the initial endowment. And that concludes our tutorial discussion.